Friends, welcome to the 48th lecture on Advanced Steel Design course. Here we are going to discuss about more on curved beams. We will also talk about finding out the stresses at different cross sections of curved beams. So, we will talk about M factor. We will also learn more about the crane hook analysis. Okay. So, we will say example 1 for this lecture. We will take up a section an unequal I section is a very common case for curved beams applied with large moments. Write down the properties of these. This becomes my plane of reference OO, and we will mark the centroidal axis somewhere here. We know this distance actually is always measured as R, and we call this dimension as B1. This as R1 and this as R2, and of course this dimension as R3, I am marking it here. And this is okay, this is R4 and this is R3. This is B1, this is B2 and this is B3. Okay. This is piece number 1 for us, 2 and 3 for our reference. Then we will cut a small strip which is measured the distance y from here. We call this as dV, where this distance is V from here. Okay. So, general expression for MA is given as integral y by R plus y dA. From this figure, we can easily say y can be replaced as V minus R, V minus R by V integral dA over d, which becomes integral dA over A minus R integral dA by V, which is MA. So, now MA is equal to A minus. So, I have got different components. Let me, I think, copy this figure, it is better. I will copy this figure. put it here, then I will write MA here. MA is going to be, equation is dA, which is A minus R times of, see we have integral over the entire area A, I am dividing into 3 parts, okay. So, R times of, okay, I will do it here, minus R times of, let us do from integral R2 to R1. So, that area will be B1 dV by V, okay. See here, I am doing it for dA. So, small strip cut here and that strip is going to vary from R1 to R2, that is what I am doing, okay, plus integral R3 to R2, for this strip it is B2. Similarly, integral R4 to R3 and this is B3. Okay, which will now become A minus R times of B1 ln R2 by R1 plus B2 ln R3 by R2 plus B3 natural logarithm 4 by 3. So, now M will be actually equal to 1 minus R by A of this equation and E will be R minus A of this equation, okay. So, you can easily calculate this. So, therefore, friends, if I have a general expression for rectangular sections, E will be R minus A by of summation of I equals 1 to n, n is the number of components of rectangle present in that, Bn ln Rn plus 1 by Rn. This is what I get E as general expression. Okay, let us take a triangular section now. So, we will draw a triangle. Plane of reference, triangle has value B1 here and this is R1 and this value is termed as R2 and triangle has a CG somewhere here and we mark that distance from here as R. Let us cut the strip. At a distance y from here, let the thickness of the strip be dV and the strip be measured V from here. Okay. Let me draw the frustum of that separately. I will mark this distance as x because I want to find the area, that is tricky here. Let me mark that figure separately. Okay. So, anyway this is getting converged to become a triangle, right. So, this is x and this is B1, right. Let us say this is R2 and this is R1. Okay. So, we now write a relationship R2 minus R1. The variation is for B1 by 2, is it not? If you look at this triangle, let us say I am looking for this part. For a variation of R2 minus R1, the horizontal arm is B1 minus 2. Okay. Now, we know that this strip is at V. This is at V. So, therefore, for R2 minus V, this value will be x by 2. So, now x by 2 into R2 minus R1 is B1 by 2 R2 minus V. So, can I say x as B1 times of R2 minus V by R2 minus R1? Okay, that is my x. Width of the strip is 2x, sorry x, sorry, okay. Now, MA is integral dAA minus R dA by V, which is going to be A minus R times R2 to R1, B1 times of R2 minus V by R2 minus R1 of dV by V, which will now become A minus R B1 by R2 minus R1 of integral R1 to R2 R2 minus V into dV by V. Which will now become A minus R B1 by R2 minus R1 of integral R1 to R2 R2 dV by V minus integral R1 to R2 dV. Okay, which now become A minus RB1 by R2 minus R1 of R2 times of natural logarithm R2 by R1 minus R2 minus R1. If we evaluate this integral, this is what I will get. So, M will become 1 minus R by A of R2 B1 by R2 minus R1 ln R2 by R1 minus B1. So, that is my M value for the triangular section. Once I have a M value, I can find a E value using this relationship R minus A by R2 B1 by R2 minus R1 ln R2 by R1 minus B1. That is my E value to locate the neutral axis. Okay. In the same logic, let us do for a trapezoidal section. This will be the plane of reference. Let us say this is B1, this is B2, R1, this is R2. Let us say this has got a CG somewhere here. So, this becomes a CG axis which is measured at a distance y from the plane of reference, measured r from the plane of reference, that is the radius r. Okay. Then we will also then mark a strip at a distance y from the centroidal axis. We call this as dV, and let the strip be cut at a distance v from the plane of reference. Okay. Now, I divide this into a segment like this, and I will extrapolate this separately. Okay. Then I can write the similar triangle equation for this, which will be R2 minus R1 on the height gives me the variation as B1 minus B2. Am I right? Okay. So, if it is R2 minus V, let us call this variation as x. R2 minus R1 into x is B1 minus B2 into R2 minus V. Therefore, x will be R2 minus V by R2 minus R1 of B1 minus B2, okay, plus B2, because I am looking for this distance as x, right. Okay. So, that is my x value. Okay. Having obtained this, I can now use the standard relation MA is integral dA minus R integral dA by V, which will become A minus R integral R2 to R1, which will be B2 plus B1 minus B2 of this, which will be B2 plus B1 minus B2 by R2 minus R1 of R2 minus V, okay, of dV by V. Okay. Which will become A minus R integral R2 to R1 B2 dV by V plus integral R2 to R1 B1 minus B2 by R2 minus R1 of R2 dV by V minus integral R1 to R2 B1 minus B2 by R2 minus R1 of dV. Okay. So, now this will give me A minus R B2 ln R2 by R1 plus B1 minus B2 by R2 minus R1 of R2 of ln of R2 by R1 minus B1 minus B2 by R2 minus R1 of R2 minus R1. This gets cancelled. So, now I get this value as MA equals A minus R times of B2 ln R2 by R1 plus B1 minus B2 by R2 minus R1 of R2 ln R2 by R1 minus B1 minus B2. So, I will copy this expression. So, I can say which will be equal to 1 minus R by A of B2 ln R2 by R1 plus B1 minus B2 R2 minus R1 of R2 of ln R2 by R1 minus B1 minus B2. That is my M, which is the modified area. Now, I can easily find E as R minus A of ln R2 by R1 plus B1 minus B2 by R2 minus R1 of R2 of ln R2 by R1 minus B1 minus B2. That is my shift of the neutral axis from the centroidal axis, which is equation 4 in our original derivation. Okay. So, friends, if we call this as equation 4, in this equation, if B2 is 0, okay, what is B2? See the figure. If B2 is 0, we get a triangle, is it not? This equation will reduce to that of a triangle. If B2 and B1 are B, see this figure, if they are B, it will reduce to a rectangle. This equation will reduce to a rectangular section. You can check that. I leave it to you, please check that and check the derivation carefully. So, there are some comments which we need to highlight very clearly before we do some more numericals. E is always measured from, okay, from the centroidal axis. And E, it is the distance of the neutral axis from the centroidal axis. Positive value indicates that E is measured towards the center of curvature. That is very important, friends. Okay. So, now for curved beams, there are some more simplified equations given in the literature. Let us also try to appreciate them and see. So, Wilson and Curian have given simplified form of equations to find the stresses in extradas and intradas of different cross sections, and say the equation is given by sigma is equal to k times of applied moment H by I. So, they say the stress, you have to use Ki. So, Ki is a factor for intradas, which is Hi minus E by Ri divided by MHI by 2I. Ko is a factor used for extradas, which is HO by E by RO divided by MHO by 2I. So, now I will give you the values of these tables as recommended by these researchers for our usefulness. Let us say I draw the shapes here. This is my plane of reference OO. I write here plane of reference. Okay. So, let us say circular section. And for elliptical sections, because elliptical sections are also not coming very common now, because they have a lot of advantages on eddies. Okay. We will talk about this shape in some other future lectures. So, let us say we know if this is my centroidal axis, we know the measurement of the centroidal axis always R from the plane of reference. Okay, this is also R from the plane of reference, and from the CG we call this as H, this also has H because it is symmetric, and the major axis H, minor axis H again. So, he is trying to work out only in the stresses in the intradas and extradas, okay, only here, not anywhere in between. So, he has said the values of R by H, and he has given the coefficients Ki and Ko. Then he also compared E when the beam is under pure bending. So, let us see what are these values given by the researchers. So, at different intervals of 1.2, 1.4, 6, 8, 2, then 3, 4 and 6. Ki 3.41, 2.40, 1.96, 1.75, 1.62, 33, 23, 14, Ko 0.54, 60, 65, 68, 71, 79, 84, 89. E value is also given in terms of R when the beam is under pure bending. It says it is 0.224 R, 0.151 R, 0.108, 0.084, 0.009, 0.030, 0.016 and 0.0070. Okay. For rectangular sections, this table is again given in a different format, becomes the plane of reference. So, OO, we draw a rectangle. centroidal axis, measurement r from the plane of reference. Let us say this is h, this is also h. So, r by h, ki, ko and e when the beam is under pure bending. So, 1.2 ko 0.305 r, 0.204 r, 0.149 r, 0.112, 0.090, 0.041, 0.021, 0.0093. So, this is not a very interesting reference. My own book, Advanced Steel Design, written for CRC. Please refer this book to get more details about the experimental studies conducted by the authors and how they obtained these coefficients. Let us do couple of more examples on circular sections. Let us say we have a curved beam, we have an applied example now. Okay. So, let us say there is a curved beam as shown in the figure here. We mark the gray. Okay, let us have it like this, it is better. Let us mark the cross section. This is 40, this is 20. Okay. Let us say this radius is also 40. This is central axis. Okay. Now, I call this as my O plane of reference because the curve is measured from here, and for the center, okay, I will mark R as usual. Okay. I am doing an applied example. Now, let us draw this cross section separately. So, the cross section has got 40 parallel to plane. See, 40 mm is parallel to OO. So, let me draw the line OO, let us say from the edge, see from here, this cross section is 20 and this is 40. Okay. Okay. The CG from here is R, which is 60. Am I right? Because this is 40 and furthermore another 20 is become 60. So, we now say R1 is 40 and R2 will be 80 and B. So, we say B is 20, okay. R1 is 40 and R2 is 80 and R is 40 plus 20, which is 60 mm. Let us say this is subjected to a load P, which is about 20 kilonewtons. Okay. Now, this 20 kilonewton P will try to compress this ring. Okay. So, M caused by this load will tend to close the curvature. It will reduce the radius. Okay. Under that condition, extradas will be under tension and intradas will be under compressive stress. So, compression is negative for us. Okay. Let us try to find out the direct stress. What will be the direct stress if you do not apply a curved beam concept, which will be simply P by A, which will be minus 20 into 3 by 40 into 20, y minus compression. Okay. So, minus 25 Newton per mm square, we say negative stands for compression. So, we can find the bending stress. Now, M will be actually P into R, which will be plus because it is tending to close the curvature. So, 20 into 60 by 10 power 3, which is 1.2 kilonewton meter. Okay, why it is positive? The moment is positive because it decreases the curvature. Okay, that is the reason. Now, we want to find for the rectangular cross section, what is the modified area? MA. Okay. You have the equation. M is given by 1 minus R by A, B, ln of R2 by R1. We have a standard equation for this. So, 1 minus R by 40 into 20, that is A, B is 20, see here we already said that B is 20, of ln of R2 by R1, which will be 1 minus 60 by 800, 20 ln of 80 by 40, which will become minus 0.0397. So, E will be MR by M minus 1, which will be minus 0.0397 into 60 by minus 0.397 minus 1, which will become plus 2.291 m. So, there is a shift of neutral axis from the centroidal axis by about 2.3 millimeters, though it is small, but look at the cross section, it's only 40 by 20. So, further cross section is significant. Okay. So, E is plus 2.291 mm. It means positive indicates that neutral axis is shifting towards the center of curvature. Okay. So, I have a cross section which is 20, 40, there is a central axis, this is my CG. I mean neutral axis is shifted down by a distance 2.291 m. Okay. And for finding out the stresses for inter-DOS, we know the equation, which is minus m by AE HI minus E by RI, which is compressive. Okay. Remember, H is always measured from the centroidal axis, not from the neutral axis, please understand that. So, let me substitute that. So, sigma B bending stress inter-DOS will be minus 1.2 10 power 6 by 40 into 20 of 2.291 of 20 minus 2.291, okay, by Ri, which is 40. Okay. So, I can get this value, which is minus 289.87 compressive. This is inter-DOS. Let us do this for extra-DOS. So, bending stress at extra-DOS, that is this point, will be plus m by AE H0 plus E by R0 tensile. So, I should say plus 1.2 10 power 6 by 40 into 20 into 2.291 of 20 plus 2.291, because you know this is 20, okay, divided by 80, that is R0, RO, we already have it here. Okay. And this stress is plus 182.43 tensile, okay, extra-DOS tensile. So, I have the hook coming here, the ring is subjected to compression. So, this is the moment. So, extra-DOS will be in tension and inter-DOS will be in compression. So, we have these values with us. Okay, friends. So, therefore, the total stress will be stress direct plus stress bending. So, if we want to find at point A, which is minus 25 minus 289.87, stress at B, which will be minus 25 plus 182.43. So, B is any point on extra-DOS and A is any point on inter-DOS. Okay, I can find these values in Newton per mm square. This will be compressive, this will be tensile. So, one can also see here the stress at extradas and stress at intradas are not equal, which means the stress variation is also non-linear. So, you cannot predict that. You have to find the exact fiber distance and then keep on working out the stresses. Okay? So, friends, in this lecture we learnt the modified area equation for different sections. We have also learnt the stresses to find in extradas and intradas by researchers. We have also did applied example of a ring under load, compression load. So, in the next lecture we will do some more examples on rings and crane hooks, etc. We will use MATLAB program and try to find out the use of Winkler-Bach equation in large initial curvature problems and try to solve and find the stresses in the sections across the curved beam. Okay. Thank you very much and have a good day.